Here we have 3 more problems in real analysis. So the first problem here is the easiest of the 3 that I've picked, and we want to prove that the set of irrational numbers is not an F sigma set. So remember, an F sigma set is a what? Is a countable union of closed sets. And we want to show that the irrationals cannot be written that way. So for the time being, we're going to suppose that it is, and then proceed by contradiction. So suppose that the irrationals are a countable union of closed sets. Well, by De Morgan's law, we know that the rationals, if this is true, we can rewrite them as an intersection of open sets. But this is a contradiction, because we know that the irrationals is a countable intersection of open sets. But this set is equal to intersection negative infinity up to Qn union Qn to infinity. I'm running out of space. N equal 1 to infinity. So they're 2 G delta sets. But then what does that mean? It means that if we were to take the intersection of these guys, we would get the empty set. So if we intercept the rationals with the irrationals, we get the empty set, which implies that the empty set is G delta. Wait, is that okay? Oh, well, okay. We have to be a bit more careful. It would be the countable intersection of open dense subsets. Open dense subsets. But this contradicts the bare category theorem. My pen is dying. Bare category theorem. And so we're done. Not a super difficult problem, but it was on a qualifying exam, believe it or not. Kind of a while ago. I think it was, looking at my notes, it seems that it was posed in the January 2017 qualifier. So this one was kind of a freebie, so to speak. Second problem. I know it says 4 at the top, but I had planned to do 5 per installment, but it was too much to do 5 in one video, so I ended up doing 3. So I saved this one for right now. So we want to prove something about sequences. We have A1 equal to 1. We have a sequence Bn that tends to 0. And we define An recursively. So we have An is equal to n minus 1 over n times An minus 1 plus Bn minus 1 over n. And we want to show that the sequence An tends to 0. All right. So what do we do? Well, we'll write down everything that we know. So we know what A1 is. It's equal to 1. But what's A2? A2, if we just plug in the stuff here, we'll see that we get 1/2 A1 plus 1/2 B1. Fair enough. So what about A3? A3 is equal to 2/3 A2 plus 1/3 B2. But we know what A2 is. A2 is this guy. So if we plug that in there and simplify using algebra, we'll get 1/3 A1 plus 1/3 B1 plus B2. And now this pen is dying too. Oh, okay. I'm pretty sure this pen's good. Someone needs to buy me pens because I'm running out of money to buy pens. And we'll do another one just for clarity. If we want to do A4, we'll have 1/4 A1 plus, or excuse me, sorry, 3/4 A3. 3/4 A3 plus 1/4 B3. And we know what A3 is because we just calculated it up here. It's this guy. So if we plug it in and do some simplification, we will see that A4 is equal to 1/4 A1 plus 1/4 B1 plus B2 plus B3. And so now the pattern should start to emerge. The pattern is that AN is equal to 1 over n times A1 plus 1 over n summation I equal 1 n minus 1 BI. All right, so now we've rewritten our sequence AN in a slightly more manageable form. We can see that as n tends toward infinity, this first term is going to die because A1 is just equal to 1, right? So I can rewrite that as 1 here. So 1 over n is definitely going to tend toward 0. That part's fine. But the issue here is what happens here because we don't want this sum to overpower this 1 over n. So we have to be careful. So what should we do? Let epsilon be given. The mantra of every analysis problem. We let epsilon be given. But we know this Bn tends towards 0, so I can write the following. There exists n, some index, such that for all n bigger than or equal to n, we have that the absolute value of Bn is less than epsilon. That's because Bn tends towards 0. So for little n bigger than or equal to big N, what do we have? Well, we can split this guy up in a way that can help us. So we have 1 over n times, and then we're going to take our summation up to the n minus 1 term. So what do I mean by n? I mean this n here. So we're going to take it up to the Bn minus 1 term. Plus, and then the rest of the stuff will go over here. So I have 1 over n Bn plus b to the n minus 1. So I've taken this sum and I've just rewritten it down here. It may not look like it at first, but I've just rewritten it because, if I expand this, and I have b1 plus b2 plus b3, so on and so forth, all the way up to n minus 1, I can rewrite it this way. And I guess I also include this 1 here. I don't know why I do that. When I did this homework problem, which I have it over here for reference just to keep me honest here. I'm not entirely sure why the 1 is included, but I don't think it matters because you'll notice that this first term here, if we call it S1, and we call this second term here S2, we can see that S1 tends to 0 as n tends toward infinity. And it's because this sum here is always finite regardless of what little n is doing, because you stop at big N minus 1. This n is not tending toward infinity, the little n is tending toward infinity. So you look at the first n terms. So this is some finite number, and then you have this 1 over n shoot towards 0. So this gets smaller and smaller and smaller. Our attention now turns to what does S2 do, because this is tending towards 0, but this guy is getting bigger and bigger and bigger. Your sum is getting larger. So what should we do? Well, notice that S2 has how many terms? N minus big N terms. Because we got rid of n terms here, that's this n here, and we have a total of n in total. So it's n minus big M, or big N. Furthermore, for I between big N and n minus 1, we have BI, I should put this in absolute value. Well, I feel like it should be an absolute value. Are my B's positive or negative? I guess I really don't know. I just know that it tends towards 0. So I have that BI is less than epsilon over 2. Although if it's negative, that's also true, so I can just get rid of it here. We have BI less than epsilon over 2, provided that something happens. So I have to make sure. Yeah, I think I need an epsilon over 2 here in order to say that. I don't think I necessarily know that, because if I want this to be less than epsilon over 2 and n is bigger than big N, which is I certainly have here, I know you can choose big N large enough where that happens because it converges. But I think to cover my height, I'm going to say that. If I made a mistake here, please catch me, because it has been a while since I did this problem, but I do remember the general trick to do it. Okay, so because we know that BI is less than epsilon over 2, and I have n minus n terms, if I just plug stuff in just to get an upper bound, I see that S sub 2 is less than n minus big N divided by n times epsilon over 2. Remember, this is how many terms I have. Here's how big they are. And then this little n comes from this n over here. But this thing is less than or equal to epsilon over 2. Which is just epsilon by another name, right? So this tells me that S2 has to tend towards 0. And that's the end. We can show that AN tends towards 0 as n tends toward infinity. The only part here that I'm a little bit sketchy on is choosing this guy up here so that I can say this down here. Because I do know that this S2 has to be bounded above by this epsilon. And I know that this value here is less than 1. So I get this value here less than epsilon over 2. But there's just something about it that just makes me a little queasy, and I can't really put my finger on it. But I think this is relatively good. Alright, next problem. So this problem's a little bit difficult. I believe the solution is on Stack Exchange somewhere. I'm not really sure where on Stack Exchange, but it was an old qualifier problem. The problem, if you know what you're doing, isn't too long, but it requires like 3 tricks in it. And to come up with those 3 tricks, if you're, a first-year graduate student, can be kind of daunting. But what does it say? We have a sequence of Lebesgue measurable functions. The supremum of the integral of fn squared is bounded above by 1. And we know that fn tends to f pointwise. We want to prove that the limit of this integral is equal to the integral of the limit, which I just write as fx over x. Okay, so let's do it. Proof. I believe this was also given to us as a homework problem. It was an old qualifier problem, but we were given it as a homework problem one semester. And I remember the guy that did it up at the board. I think he told me he found it on Stack Exchange. So the first trick is to apply Fatou's lemma. So what does Fatou say? It tells us that this integral is less than or equal to lim inf as n tends toward infinity 1 to infinity fnx squared dx. And that's bounded above by 1. I know I probably say some things that confuse you guys, like, oh, it was a homework problem, so-and-so did it up at the board. It's kind of the way that our class is structured. So the way that we get graded is that he assigns homework problems, and then on some day of the week, we have to go up to the board and present the homework problems, and we get to pick and choose which ones we do. So we're all trying to do problems and figure out which one we can do and try and get our points by doing it up at the board. And if we solve a certain amount, then we basically get our A for the semester. And I was trying to do this one, but it was too tough for me. And then that one guy found the solution on the, I mean, a lot of us kind of just end up looking stuff up on the internet if we get stuck, which is a natural, I think it's a good thing to do. Some of our instructors encourage us to do it because, I mean, personally speaking, this is just me speaking, I don't see the utility in beating your head against the wall trying to solve a problem that you're clearly unable to solve. And it's better to, I mean, it's good to work on it. Obviously, you get some benefit from it, but at some point you just need to get the answer. And then once you have the answer, you use those tools in future problems. So I don't really have a problem looking stuff up on the internet. As long as I don't mindlessly copy it down and then forget it later, because that's like I mean, obviously that's not what you want. You want to incorporate those tricks into your trade. So anyway, that was a bit of a tangent. So we apply Fatou's lemma and we see the following result. And then we know that from this result, that if we take the supremum of integral from 1 to infinity f minus fn squared dx, if we just multiply all this out and then pass the integral through and just take the absolute most crudest bound that you could take, we can see that it is at most 4. And that's because of the 1 over here. We have 4 terms here. Okay. Fix epsilon between 0 and 1. Now, why are we going to do this? We're eventually going to set up a sequence here, and we want to show that the sequence is arbitrarily small using this epsilon. That's kind of like the one trick for like every analysis problem. So the first trick for this one was using Fatou's. The second trick happens now. So we want to apply our good buddy Igorov's theorem. We want to apply Igorov's theorem. So what does it say? There exists a set E inside the interval from 1 to 1 over epsilon, such that the measure of E complement in the set, so 1 over epsilon, get rid of E, is really small. And we have uniform convergence on E, right? Yeah. Fn converges uniformly to F on E. All right. Now I'm going to subtract this over and rewrite the integral in a nice way. So we have integral Fn x over x dx subtract integral 1 to infinity fx over x dx. And that is less than or equal to, okay, using Igorov's theorem, I'm going to rewrite this as a single integral and split it over the two sets, E and E complement. So we have integral E Fn minus F over x dx plus integral, and then we have this really annoying set, which I have to write out explicitly. 1 over epsilon, get rid of E, and then I want to union that with the stuff outside of it. And we have the same stuff inside, right? Fn minus f over x dx. Whew, that's a lot. Okay, so I'm going to call this first integral I1, and we'll call this integral I2. So clearly, the very dangerous word clearly, I1 tends to 0. Why is that clear? It's clear because of uniform convergence. I believe that's a result that we can apply. Now the issue is, what do we make of this integral? For this integral, we need to use the third trick. So the third trick is Cauchy-Schwarz inequality. So, by Cauchy-Schwarz, we have that I2, steady my camera, is less than or equal to the integral from 1 to infinity of fn minus f squared over 1 dx. Then we take the 1/2 power, multiplied by integral 1 to infinity. And now, if I integrate over this set, since I've included the fn minus f part squared over here, this just becomes the characteristic function over this really annoying set to write. 1 to 1 over epsilon, get rid of e, union everything else. And that's all over x squared dx. All right, and now we apply our really crude bounds. So we know that for the first integral here, we know that this guy is at most 4 inside the square root, which gives us a 2. So this guy is at most 2. What about this guy? Well, the integral from 1 to infinity of x squared, I believe, geez, I should know this. I mean, just use calc. I think it's 1. I'm showing my calculus ignorance, but I'm pretty sure it's 1. I mean, oh God, okay. So x to the negative 2, you add 1 to the exponent, divide by the new exponent. Yeah, it should be 1. So when you integrate over that set, over that over this dude, we end up with the measure of the set. So we have the measure of 1 to 1 over epsilon, get rid of e, union 1 over epsilon to infinity, plus epsilon raised to the 1/2 power. Oh, I forgot my 1/2 power up here. So we have the measure of that set. I'm a little bit sketchy as to where the epsilon comes from. Hold on, let me just make sure that I haven't said anything horrible. Oh wait, the epsilon comes from, now I've talked myself out of it. Let's see here. So I understand that this is the part of mathematics that's really annoying. You move along and then all of a sudden you just get stuck somewhere. So I need to resolve this epsilon. How do I do that? Because this returns me a 0 or a 1 depending on if I'm in this set or not. So that's just kind of a constant. So it should be, hold on, just give me 1 second here. Oh, you brilliant man, you're able to get to the right page. It's staring me right in the face and I don't see it. Oh, I'm a moron. I'm a moron. This set here has size epsilon. That's where it comes from. Okay. So we end up with this guy. I mean, that's from Egorov's theorem up here somewhere. Where is it? Egorov. Right here. That's where it comes from. So I have that guy. And then what do we know about the measure of this set? Well, I know that this is bounded above by 2 times the square root of 2 times epsilon. Square root of 2. So because of this is just constant times epsilon, we can see that together this implies that I2 has to be tending to 0 as epsilon positive was arbitrary. And I believe that finishes the proof. So this was a good example of a problem that's kind of difficult if you're not well practiced with it, as well as, you know, you get to the very end and then you get stuck. And then hopefully you'll get that resolution, especially if you have resources to look stuff up in. But I hope you found this useful. I'll plan on doing more problems like this and post it to the channel so that you can see what our day-to-day problem-solving life is like in a PhD program. Anyway, thank you for watching.